Today, we're going to talk about modeling a reservoir with multiple operating pools, and um, this is lesson 8 of the water management modeling series. Next week, we will be talking about modeling a tailings facility, and we'll have a guest speaker. So, if you're doing mine water balance modeling, I highly recommend coming to lesson 9. The guest speaker will be Nicholas Brink with Stantec. All right, so with that, I'd like to get started here, and I want to show you an example that I will come back to explain further in the details, but I just want to show this model that when we run it, well, before we run it, first of all, we can specify um, the zones, the operating zones within this reservoir shown in this diagram. And these can be specified as levels, for example, levels where the zone begins and ends. And then you can use this to simulate the process of operating the outlet facilities on a dam, for example, or also, or I should say, or controlling inflows coming in based on where the current water level sits in relation to these various pools. And so what we'll talk about today is how to build that type of logic in GoldSim. Um, we will be building on subjects that we covered in previous lessons a little bit, but then just building on those. Mostly just talking about how to control discharge from a reservoir, but we will be doing it in a way that's kind of coordinated with others to create these operating pools. Okay, so when you run the model, then you can show a plot that shows over time how the water level is sitting in relation to these other demarcations. So for example, there's this dashed line at the bottom representing a dead pool in which we would not allow any controlled discharges uh, from the reservoir. And then as we might rise up above this first solid red line, this would indicate a point at which we want to start running some controlled flood discharges. And what we're trying to avoid is crossing the next line up, which is which represents the spillway crest, and at which point we would have uncontrolled discharges and potentially put structures downstream at risk, for example, that kind of thing. So you'd have competing uses of this in this reservoir. One being that it's providing flood control from, for example, stormwater runoff coming into this drainage or something, and you're wanting to control those. But then in addition to that, providing some water supply to downstream users. And so you could use, in this example, it's using a guide curve, that's this black line, where we try to stay above this curve, and if you start to approach it, then you can make reductions in the water being supplied from the reservoir. So those are the kinds of things that I'd like to talk about, but I need to start with a more basic example so that you can see more easily how this kind of thing can be built. Okay, so in this example, it's a simple model that I've started with just some inputs, and we're going to build the logic into the model to work with these inputs. What we have is the main one being an inflow that's changing over time. I'm using a stochastic element to pick random numbers for demonstration, but in a real model, you might be calculating this, or you might have a forcing function in the model that is just a time series of inflow values that perhaps you measured over time and want to use those for some future scenario or forecast model. Okay, so with that, then what we want, obviously, the first thing is to create the element that represents the reservoir. And the best way to do that nowadays with GoldSim is with a pool element. As you might know, this is a newer element from where we used to only have the reservoir. The pool element provides some additional functionality that makes it very handy for simulating reservoirs, especially when you have more than one outflow. Okay, so I'm going to call this reservoir and give it units of cubic meters. with flow units, corresponding flow units of cubic meters per day. I'm doing this just because it makes it easy. I have 1-day time steps, so I can work with small numbers and show the same time scale in my flows. Uh, for when you're building a prototype model, for example, perhaps you want to see if GoldSim can do what you need it to do for a certain project, and you just need a small prototype, or you need to show it to your team and see if they agree. I think it's always good to start with simpler units like that, even though you might be moving on to, for example, liters per second or CFS or GPM or some other thing. It's just nice because it makes it a lot easier to check your answers as you're building the model. And then you can always change units later. But anyway, what we want to do here is first, let's start off with the initial quantity. So we're already given, as you can see up here, it says initial level. This is a depth, water depth measured from the bottom of the reservoir. So we're going to use that to determine our initial quantity, but obviously that's not the same units. We need a volume. So we can get a volume with a relationship table, and that's shown here. So if you open up this table, it's a volume to elevation table, and if I click on edit data, you see that the volume numbers are shown here. Also note that it says volume in the header, and that's because when you define a lookup table, they're just generic, but you can type a name for your independent variable right there. If you have a two-dimensional, then you can give names to columns and so forth, but we just have a one-dimensional lookup table. It's a linear lookup, and we just put in here the volume amounts in increments, in cumulative increments, and then the corresponding depth that is associated with those volume amounts in the reservoir. And so obviously in a real model, you'd have a lot more points than that. But just one thing I wanted to note, and you will see this in the next week's presentation on tailings facilities, and that is that this table could be changing over time, it could be dynamic. Now we're not going to go into a lot of detail on that in that presentation, but we'll make note of it, and there have been other webinars given on this subject that will be pointed to. But anyway, this doesn't have to be a constant, but it is in this model. Okay, so we want to convert the initial level to an initial volume just by using that relationship. So we'll go ahead and do that now. So I'm just going to refer to the volume elevation table and then the initial level. Now, doing this type of lookup is actually backwards because we need to give it a volume and have it return a depth. Well, it turns out that you can do a reverse lookup on the lookup table simply by going in here and adding a second argument. It's an optional second argument. You can right click, go to constants, find table constants, and get the table inverse. Okay, so that's one way. You could also just start typing TBL. I wonder if we can do it this way. No, we can't. Okay, that's just for run properties. Anyway, you'd have to spell the whole thing out. TBL inverse. And so what that'll do is adds a second argument that causes the lookup to do it in reverse. So we can give it a depth, and then it will do a linear interpolation to find the corresponding volume with that. And that's how we can define the initial volume. The next thing we want to do is add the inflow into this reservoir. That's really easy. Just reopen the reservoir and go to the inflows tab here, click add, and find the inflow. I just double clicked on that. It's added. And now you can see GoldSim drew an influence there. Okay, now that we have that, we can now run the model and just see how it does. There's a warning because I have a chart over here that I need to add some additional elements to link to it. So don't worry about that warning right now. But if we open this up, and actually I do need to. Let's see, I'm just going to temporarily add the reservoir volume right here, and that's going to be the cyan colored line. And so what you can see here is, and don't worry about these other two lines, just the cyan. You can see that it's, and well, we're using the Y2 axis. I suppose this is a bit complicated, more than I wanted, but essentially we're starting out here at about 4,000 cubic meters, then it rises up to almost 14,000. but we want to control the water level in here at about, I think it's 5,000. I'm pretty sure. We don't want it to go over 5,000. You might have noticed that's what was in the lookup table. That's the top of the dam, right? So we don't want that. So we need to build in some logic that will control the volume and prevent it from just running away from us. And so that's what we're going to do now with the spillway flows. With this one, I want to use a rating curve. And we talked about this, like I said, in a previous example. And so I'm just going to do, well, there's actually, um, there's a couple of things I'm going to do in here. The first one is that we want to calculate a spillway discharge flow rate using this rating curve. So if I open it up, you can see here that we have independent variable of depth. And this is the depth over the spillway, by the way, measured up from the spillway crest up to the water surface. As it gets closer and closer to 1 meter, then this flow goes up to this value. Obviously, this would have to be a very narrow spillway, not very realistic. But anyway, the point is that we have a rating table here that we can use to calculate the flow that we would expect. So let me just go ahead and type in a new expression and call it spillway request. Just gonna shorten the word. If you ever shorten words, you should always, of course, put this in the description just to make sure everybody is aware. Okay, so cubic meters per day, and now I'll just do a lookup on that, but I can't do the lookup yet because I need the depth. I need to measure the depth above the water depth above the spillway. So I'm just going to add a new expression and give this units of meters and call this spillway depth. And so now all we have to do is get the, we have to calculate the, oh, I didn't calculate the water depth yet. That's right. Okay, so the next thing we have to do actually is we need to know how deep the water is measured from the bottom of the reservoir. And we can get that from the volume elevation table. So let me put that expression in as well. Call this water depth. And so now we're just going to refer to, again, to the volume elevation table and then the volume of water in the reservoir, which is just the main name of the reservoir. So we put that in, and now we've got the water depth, and now we can just subtract the water depth from the spillway level to get the depth of the water over the spillway. So water depth minus spillway level, and perhaps a better name for that might be spillway crest elevation. But anyway, I guess it all depends on where the datum is. But anyway, the point is this is the constant, the depth from the bottom of the reservoir to the crest of the spillway, and we are subtracting from the water depth that value to get the depth over the spillway. But because sometimes the water level is below, or most of the time it's below the spillway crest, we are going to have a negative number here. So to prevent that, I'll just put a max function in here. Like that. So it'll only measure a value above 0 if the water level is above the spillway. Okay, so now that we have the spillway depth, we can refer to that in the spillway rating curve. Oops. Okay, start over. Spillway rating table and spillway depth. Okay, and then what we can do is we can add this spillway request to the outflow of the reservoir. And when we do that, we want to give it a name that makes sense. So I'll call this spill. Notice I'm in the outflows tab of the reservoir or of the pool element. And then I just refer to the spillway crest. Request, sorry. All right, so now what we should see is that whenever the water depth rises above the spillway level, then we will start discharging at a very high rate. But there is something important that I wanted you to see with this, and that is we have oscillations. Before we get into that, let me just switch the value that we're looking at. I'm going to connect to water depth here, and I'm going to remove the volume. We don't need to see that. Okay, so what's happening here, and we're just looking at the depth now in red. What's happening here is the water level rises above the spillway level, and then the rating curve gives us a very high flow number. So it causes it to provide a flow rate value that when applied over a 24-hour period, which is our time step, ends up being more than what we can deliver above the spillway, therefore dropping the water level below it, and then causes these oscillations. So these can cause problems, especially if you have many ponds or reservoirs connected to each other. So what you want to do here is put a check on this, where you say we cannot discharge any more than the volume of that slice of water that is sitting above the spillway elevation. So I'm going to put in here a value that's referring to the volume of water above the spillway, if the water level rises above it. Okay, so I'm going to call this spillway volume, just to indicate that's the amount of water above it, cubic meters. And now what that means is I need to know, first of all, what's the total volume that we're having, the whole entire reservoir, and subtract that from the volume that we would have at the constant value of the spillway crest. So I just need to do I need to do one more lookup on that lookup table, volume elevation table, and then we refer to the spillway level. And because we're doing a reverse. If it makes it easier in your model, if most of them are inverses, you can always switch the table, or actually copy the table and then switch the columns. Now I just need to come over here to the front end of this equation and subtract the volume of the reservoir, which is just called reservoir. So I subtract those two, and then that would give us that volume. But what if the reservoir volume is less? Well, then we get a negative number. So we need to prevent that by putting a max again in here. Go to the end, like that. Okay, so now what we can do is we can calculate the minimum value of this and what we've already calculated, and say that's going to be the flow rate over the next 24 hours. But what this means is that we're going to have to convert this volume, the spillway volume, into a flow rate. And to do that, we need to refer to some assumed time step. And I like to put a global variable in the model called dt, or something that refers to change in time, delta time, something like that. I don't use GoldSim's built-in time step length because in this case, I do want to use an average flow over 24-hour period value for these kinds of calculations. So I don't want to refer to the built-in time step length that GoldSim provides, because that is not always constant, not necessarily. Oops. Units of days, and then I'm just going to give it 1 day. Okay, so that's our time step. Then what I want to do is I want to divide spillway volume by dt, and that gives us the maximum flow that we would have able to discharge from the spillway. So then I just want to come over here and put a min function and refer to the spillway volume and divide it by dt. So it'll take the minimum of those two things. And now when we run the model, we look at the spillway request, and we are not seeing oscillations. And we can also look at the water level, and we're also not seeing oscillations there. Okay, so that's good. That allows us to control the reservoir level at the upper level, at the spillway level. Now what I want to do is build a lower level. We have this dead pool at 4 meters, at which point we turn off any water supplies, or we reduce them, in order to try to maintain a lower level and not go below a lower level. And that's the way that it allows us to build these various pools. And we don't have to end with just these 2 pools, but for this demonstration, I'm just going to show these two. Okay, so I just added a new container called water supply just because I'm going to put all the demands and the supplies, everything in there. Um, Perhaps you don't do it this way in a real model. Maybe you'll have a water supply container and maybe a water demand container separate. But just for this, I'll just have one container. All right, so the water supply, like I said, it will be on and running, and it will be a number that's just assigned to the model. But you might have it connected to other things in your model or calculated. And in mine, I'm just going to use some random numbers to calculate a water demand. Anyway, those are running all the time unless we look at the water depth and it drops below the dead pool elevation, which is 4 meters. If it ever drops below that, then we turn it off. Turn off the water supply outflow. But as soon as it rises above it, then we want to turn it back on. Okay, so to do that, we've already talked about this before in simulating outflows. So I'll just walk through it pretty quickly. We'll use a status element that we'll call discharge on. And I will turn this on, meaning we will allow water to be discharged for water supply when the water depth is greater than, and then we will say the dead pool elevation. Okay, and then I'll go down here, we'll turn off the water supply when the water depth is less than dead pool elevation. So when it drops below the dead pool, then we turn it off. Okay, and then what we can do is we have this just given water demand, it's just assumed in this example. It's just random numbers, but you might have a time series or you might have another part of your model calculating a water demand for you. In either case, we will then take a selector, use the discharge on output to then refer to the water demand only in the times that discharge is allowed or discharge is on. So if discharge is on, then water demand. Otherwise, nothing. I need to also put the right units, flow units in there. Okay, and we will call this discharge request. And then we can come back over to the reservoir and add another outflow in the outflows tab and add discharge request. I'm just going to call this one supply. I'll call it supply A. Discharge request. Okay. And then we run the model. And now what you can see here is that the water level is drawing down, and you can see that it hits 4 meters, and so it flattens out. We don't drop below. It might, in reality, it's going to drop just slightly below because the way our logic is, it's set up to say leave it on until you drop below. So it'll keep dropping below until it hits the next time step once it's triggered. And so you would see it just drop a little bit below, but not much. Also, what you might see is some oscillating at the lower level. So let's go look at what the actual discharge request is. And you can see that it is doing some oscillating right here, and that's because of our really tight band at the point at which we're turning on and off the status element. What we really want is a little bit of a dead band where it doesn't make any change to its status unless we go outside of that band. I'm going to create a band just by adding a multiplier, actually multiplying a value, multiplying a factor to this 1.25, I'll say. So this just raises up that level a little bit to the point where it'll wait before it turns on again. So what we should expect is that the reservoir level will kind of hover a little above the dead pool line a little bit more and drop down when it turns back on. So we run the model, we look at the result, and we see that it stays off for the duration of the time that the water level is within that dead band. Open this up again. So what happened here is we hit a point probably around in here where we were about 25% above, well, 1.25 times 4 meters, and then it stayed off until it rose back up above the 1.25 times 4 up there. And so then the water supply is just completely turned off during that time. So that's the difference between a rating curve approach like we use on the upper end, and the switch approach or the status approach that we use on the lower end. Both work well, but you just need to make sure that you always look for these places where you might be inserting time steps and also oscillating. And you can always see if you're inserting time steps if you go to the simulation settings and then the advanced. And if you check this box here where it says include unscheduled updates, also this first one should be checked to even allow them to occur. But you can definitely get a lot of inserted time steps if you're using bounds in your reservoir. Now we're not hitting our lower bound. Our lower bound is 0. We never hit 0, and we shouldn't, because we have this dead band that's kind of a protected range unless there was just a lot of evaporation. But it shouldn't go all the way down to 0, so we would never hit that. But if we had decided, instead of building the spillway, to just put an upper bound here, then we would get inserted events occurring. And it's okay, it's just important to note that, because GoldSim will, by default, insert a time step at exactly the point at which the volume hits the upper bound during the simulation. Okay, but we will just avoid that completely by not adding an upper bound. And so some people might say, well, you should put the value of the top of the dam. You don't want water to go over. But I would disagree with that. I don't think that's really necessary. To me, that's a bigger problem. I would say that that's a problem with the model. I don't think that'd be something you'd want to, unless you're simulating a dam break, I guess. But other than that, you probably don't want to even be considering that option. And so in that case, then you'd probably want to put a check in the model that interrupts the simulation and says, oh, hey, your water level is at the top of the dam. So this is a big deal, and you should do something different. So you could do that with an interrupt. Another way to do it is what is done in this example model that I showed at the beginning, this model. If I go into the model, then you will see that we have up here, let's see, need to move some things. Okay, I have a dam breach warning. I use a script element. Why did I use a script element? Oh, because I just wanted to, well, this, yeah, this is, I see. Maybe this wasn't necessary, but sometimes you want to write a warning to the log, to your run log, and have it include the value of whatever variable you might be monitoring, and have that be written to the run log too. And you can do that with, let me go back to edit mode. You can do that, for example, in this warning that we're adding to the run log. We do it. I'm sorry, I didn't see it in the text because it cuts off after the first line. But when you open up the text, you see that we have these curly braces with an equal sign, and then the name of an output in the model. So this is an element name in the model. It shows you here's the top of the dam level, reminds you of it, and then says here's the level at which the breach occurred, and so it puts that there. So anyway, this is a lot more complicated than what I'm talking about, but I just wanted to note that if you needed to, you could just say, you're hitting the, or maybe even you're approaching the top of the dam, and then you can put the level, refer to the element to report the level at which you did, or you could also say report the time. And this is also a reason you might want to put it in a script element, because you might only want to show um, this error message maybe at the beginning, or sorry, the first time it happens, and not show it again so it doesn't get reprinted multiple times. So you can use additional logic, put additional logic in here to do that kind of thing if you wanted. Anyway, the main reason for using a script for reporting is that you can report the value of an output and put that in your comment, which gets written to the run log. So that's all I wanted to say about that. Okay, so moving on. Now we have a model that controls flows at the low end and also at the upper end in order to create multiple operating pools within the reservoir. During the morning webinar, somebody asked if it would be possible to show a plot of the volume elevation relationship that's shown in this table. We don't have anything in this element right now, but we do have a workaround. Well, I made up this workaround on the fly when we were talking this morning, but it might be useful for you. It's not the best, but it does it provides you a way to see the relationship. And what it is a submodel. Now, if you had a dashboard out here in the main level, you could add a button that navigates to a dashboard inside the submodel, shows you the plot, and then just return by clicking a button. So for the end user, for all intents and purposes, it's very easy to see the volume elevation relationship for them. It would be very easy, just 2 clicks of a button, in fact, or 2 button clicks. But for you to build it, it means you have to put in a submodel that runs for a number of realizations that represent increments that you take from the lookup table. So in this case, this submodel, it runs for 20 realizations. So we're using Monte Carlo as a workaround, as kind of a hack to get to sample values from the lookup table to get a relationship plot. And so we run it 20 times and it's static. We don't need to run it through time, just a static calculation 20 times. And when we do that, if I go in here, it allows me to use that same lookup table. I just copied and pasted it into here, into the submodel. And you might be asking, well, can we just pass it in? Well, you can't just pass the lookup table like that in, but usually these kinds of tables aren't changing unless, again, we're talking about something like a tailings facility where it is. We have something different. But you can also just import your lookup table from a spreadsheet, right? So just if you had that link, then you would just update the values in the spreadsheet. Then these would always have the latest information. So that's one way to preserve the data if it's changing a lot. Anyway, so we have the lookup table here, and then we add the depth, the water depth, and these are increments of depth for each realization. On realization number 1, we just say multiply that by 250, and it will then create a point that represents the resulting depth at that volume increment we're adding. So you can see as realization 2, then it's at 500, realization 3, 750, etc. The reason we set those numbers is because we want to go all the way up to 5,000. And we can do that with 20 realizations. Next, we want to look at the volume increments, and we do that by realization multiplied by 0.5 meters and do an inverse lookup. And it tells us the resulting volume. So we're doing lookups in both directions, and then we just use a multivariate chart to link to the depth compared to the volume, and we get a chart that looks like this. So it's volume to depth. If you wanted to see it the other way, depth to volume, simply click on move down to switch these two, and then you get a volume to depth relationship. So that's one way to do it if you want. If you wanted to have that, you could also put that into a dashboard, like I said, making it very easy to get to that information. Okay, so in the end, we end up with this this way to control the volumes at the upper and lower end using monitoring the water level or the water depth. Okay, so this big model, the one I started with, that has this big dashboard here, you can put information in about these zones. You can also put information in about the spillway, the dimensions of it, and also the outlet works, meaning there's a pipe in here where it discharges out at some point. So you could include some hydraulic information about that, um, and then a starting level like we had. And then also in this case, it looks like we might be calculating inflows by using some sort of runoff model. Let me see if that's true. Oh no, that's just direct precipitation. Oh, okay. So precipitation and evaporation are really just used for the water surface, and we must have inflows coming in um, from just a time series. So let's go ahead and go in. Let's go ahead and look at this. And that is what we have here. We have a time series of inflow that just comes in. That's just a forcing function in this model. And then we have geometric functions. I put all of those in one place because there's a lot more in this example. We have all these different pools, and we refer to our elevation area table, not elevation volume table. It's just another way to do it. It's more straightforward to use elevation volume relationship because elevation area, we have to assume that you can do a linear integration on the table to get the assumed volume increments that correspond to those elevation increments. Um, but the GoldSim can do that on the fly for you by using another secondary argument that is called integral, TBL integral. This will allow you to do a lookup that finds the resulting volume from an elevation area table, which is kind of nice. It's convenient, but I would say in a real model, I would imagine that you probably already have the data that is elevation area and volume, or maybe just elevation volume. But anyway, I don't think you would need to go through this most of the time in most applications. But anyway, you can determine the volumes at these different zones by referring to that table and then also the constants. For example, what's the flood level? What's the initial level? What's the bottom of the dam? What's the inactive depth? All those things. So that's how we can set those up. Now that we know what those points are, it makes it a lot easier to go in here and do these other calculations. Evaporation and precipitation, that's not something we talked about, but well, it's pretty straightforward. It's really, in this case, we have monthly values, but you can rely on the modeling that we talked about in the very early lessons in this series to add precip and evaporation and so forth. But the ones we want to talk about are these two upper ones. Let's start with the flood spill control. So in here, we have two different types of, we're using two zones. One is the controlled flood discharge zone, and that's the calculations down here. This is the area where um, once we enter that zone, we want to evacuate the water from it. We want to get it down, but it's not like a risk necessarily. It's just we want to control the flows release the flows at a controlled rate, and this is, in this case, it's done using hydraulic calculation based on the pipe length, and so it requires iteration to solve because the flow does affect um, the the head loss because of friction. And so it's an iterative solution to solve that in this case. But you might not have something that complicated. You could just have, um, you could use a lookup table like a rating curve again, where the deeper the water is, then maybe the higher the flow rate would be, and it's just an approximate. I mean, we're talking about 1 day time steps anyway, so that might be close enough. But then on the upper zone, the zone above the flood zone, this is the spillway or uncontrolled flow zone, where water would just flow freely over the top of the spillway and perhaps be a more of a risk downstream. So you don't want it to be in this zone. But if it ever gets there, then you would have a mechanism to get it over. And in this case, we're using hydraulics again to calculate it using a broadcast weir flow. But still, like before, we have a limitation on that because you can get oscillations with this kind of thing. It's probably more likely to get bigger oscillations with this kind of a calculation than the rating curve we had, I would imagine. But anyway, we use that um, to to calculate the minimum of these two. We get the minimum of the weir flow and the max spill flow to calculate what the spillway, the ultimate spillway flow is, and without getting oscillations, just by figuring out what that volume of water is in that wedge that's sitting above the spillway crest elevation. Okay, so we did the same thing there, and then in the withdrawal request, um, it's actually in this case using a kind of a rating curve approach again, where we look at the target that we're trying to match in that might be changing over time, and the further we rise above that target, then the higher we can, or the higher rate at which we can deliver water. So it's a way to throttle down or control discharges or reduce discharges as the water level gets lower and lower. And it's a way to control the flows using a guide curve, which is often in larger reservoirs, or commonly used in larger reservoirs. Okay, so with those controls, we use the geometric level values, and from that are able to control the flows and link those to the reservoir. So in this case, we've got a reservoir um, with two inflows, runoff inflow and direct precipitation. And on the outflow side, we have multiple outflows. We put evaporation at the top, always highest priority, because it's not something we can control. In this case, spillways at the very bottom. You could argue, well, that's a higher priority, but it's always going to happen last. It's the last thing that we try to take. It doesn't even impact, none of the lower priority numbers would impact anything. But I like to do that just to make sure it's understood that the next highest priority as far as delivering water would be what we're giving to our water supply for our water supply. But anyway, you could switch these around easily. But really, the only time that these priorities come into consideration is when the reservoir is empty. So that's why I'm telling you it's not really going to impact us, because we have a dead pool that we're maintaining and probably will never empty the reservoir ever. That's the only time that these come into play, is when the reservoir is empty. So the way that you impose priorities on these different levels, so for example, you might have many deliveries you want to make for water demands, the various water demands, and they all have a different priority. You could do that by using levels like we have. So for example, we have one level here, but you could add a whole series of levels here, at which point you throttle off, or probably a better situation would be a status element that turns off flows that are being delivered to a specific delivery, but not the others. And it would just require doing what we did in the previous model multiple times, one for each of the zones. So with that, that covers, how you would implement the logic for modeling these different pools. Hope that was useful. And again, the next lesson next week will kind of work off of this a little bit, and hopefully be helpful, especially for those that are doing mine water balance models. I'll wait around a bit here to see if you have any questions. If not, thanks for joining, and we'll see you next week.